Okay, so welcome back. We're ready to turn to one of the most important, significant contributions in mathematics in the 19th century, the derivation of the Gaussian curvature in terms of the metric. It's called the theorem by Gauss, his excellent theorem, Theorem Egregium. And along the way, we'll be looking at what's called the consistency conditions of minority Gaussian. Okay, that'll be useful in this particular derivation of Gauss's excellent theorem. Okay, now I'm not going to do all the algebra here. This is a little bit heavy in the algebra. Okay, and we've done the algebra in the textbook. Okay, and the algebra here will be somewhat different. Okay, given the opportunity, I do this theorem in different ways each time I wake up. Okay, in the textbook, we do it by a traditional method with a very general coordinate system. Here will be a little less general, but we'll do the theorem in a particular way. Okay, which will set us up actually for discussing covariant differentiation on these surfaces. So I like this particular derivation for that. Now in the textbook, I also do the derivation from the perspective of Riemannian geometry. Okay, that's a piece of cake because Riemannian geometry really sets you up to study the intrinsic properties of a surface. So it's particularly simple. And here we'll look at it from a particular point of view, and along the way we'll introduce these Christoffel symbols to discuss the coordination of the surface itself. So if you're following along in supplementary lecture number 9, that's really where the heart of this video series is. Okay, you should turn to page 41 and follow along. Okay, because I'm not going to be able to do all the algebra in there on these posters. It's just not very appropriate. But we'll be doing them in recitation class. We'll do everything in detail there. There's a sketch of it in the supplementary lecture, but still, even there, I ask you to do some of the algebra because it's a little bit heavy going. Okay, but so let's not even worry about that. Let's just discuss the ideas behind the heavy algebra. Okay. So, Gauss's excellent theorem. What's it all about? Well, it's to show that the Gaussian curvature depends only on the metric and its derivatives. It's independent of the embedding space. Okay, it's independent of the second fundamental form. It's only dependent on the first fundamental form. A creature who lived on a surface can measure distances on that surface, and he can feel and experience and calculate the Gaussian curvature. He doesn't have to know anything about the embedding space. K is a bending invariant. Well, what does that mean? Okay, well, that means that it only depends on the metric. So if this is my surface, okay, my precious supplement lecture number 9, and I do something to it, like I simply bend it, okay, well, that operation doesn't change the metric. It doesn't change the distances, okay, between any 2 points. It's a bending, no squeezing, okay, no stretching. It's a bending. It's an isometry. It preserves the metric. And under those circumstances, okay, K is an invariant. Okay, trivial example. Here's a imagine this is flat. So this is just Euclidean 2 space, and then I take it and I wrap it up and I make a cylinder out of it. Okay? Okay? Bending invariant. So therefore this cylinder has the same Gaussian curvature as the flat Euclidean plane. I might do something else. I might make a cone out of this thing. Okay? And as long as so I make a cone like that, try to make a point down here. So as long as I avoid the edge here, where of course it's a singular edge, and anywhere inside the cone, I know that the Gaussian curvature is going to be 0. Okay, no matter how I bend it, it just doesn't matter. So I have a tremendous invariance of the Gaussian curvature, and we'll we'll learn a great deal. We'll learn a great deal about that. Okay. Okay. So let's sketch the construction. Okay. So how do I measure the Gaussian curvature along a surface? Well, usually I want to see how much it's curved as I move along the surface, and so at any point on the surface, I construct my tangent plane. R sub u, R sub v gives me the vectors that span it, and the cross product gives me the unit vector perpendicular to it, and so I really have to track how those three vectors vary across S. That has all the information in it to tell me how much the surface bends. Okay, so I want to study how this changes as I vary across S. In other words, as I vary across S, as I move along S, I move along the mesh, which I'm labeling UV. So I want to differentiate this character in the U direction and the V direction and understand how it changes. So that's what I've written down here: RUU, RUV, RVV, and then N sub U and N sub V. Okay, well I know how N sub U and N sub V behave. That's just the Weingarten map, and I've written that down before. And I know that the coefficients A can be solved in terms of the first and second fundamental forms. What about RUU? Well, so RUU, okay, that's a vector in the space, okay? It's going to have some components in the tangent space. It'll have a component as well in the normal to the tangent, right? Okay, I don't know what direction it points in. It just depends on the surface. I know that R sub U and R sub V span the tangent space, but the derivative of any one of those tangents might be off the tangent space. So I have to write RUU as a linear combination of R sub U, R sub V, and N. And that's what I've done in these cases. I've called the coefficients, these gammas, okay, look in supplementary lecture 9 for the details there, but they're just coefficients. There's a labeling on them which looks a little bit funny here, a little ad hoc. That's anticipating Riemannian labeling and covariant labeling later on, but we don't have to know about that. Okay, they're just coefficients, and I just want to use the same coefficients as we'll use when we get to more sophisticated subjects. Now there's a component in the normal direction, and I already anticipated that the coefficient there is the coefficient of the second fundamental form. Okay, well how do I know that? Well, let me take this RUU and dot it into N hat. Okay, so let's do that. This term will give 0. This term will give 0. R sub U is in the tangent plane. It's perpendicular to N hat. So when I take the dot product with N hat, it goes away. It goes away. N hat dotted into itself is 1. So I get the formula E is equal to RUU dot N. Yes, that's one of the defining relations of the second fundamental form. We derived that already. So I've anticipated that this coefficient is E, like that. And then similarly, when I do RUV, I've anticipated the coefficient of N hat is F. When I do RVV, I've anticipated that the coefficient of N hat is G. Okay. Oh my God, it looks like a mess. It looks like I introduced all sorts of unknown coefficients, but it's not true. The claim is that all the Christoffel symbols, okay, Christoffel symbols can be calculated in terms of quantities we already know, the first fundamental form and its derivatives. Okay, so let's show that. Okay, so I write the gammas, okay, the Christoffel symbols with upper index I can be 1 or 2, lower index J and K can be 1 or 2. They're not new. We can express them in terms of the metric. They do depend upon the coordination that I use, so they're not geometric objects, they're just parameters. So, okay, so let's keep that in mind. That's pretty clear from what I've already written, but some people think that maybe gammas should be tensors, maybe geometric objects or vectors. No, they're not. We've seen already that they're just coefficients for particular parameterization of the tangent plane, and there's nothing more to them than that. Now, to isolate the gammas, what I do is I take the 6 equations I've written down on the other poster, and I just project them into the tangent plane. Okay, so I take my equations for r sub u and I project it into the direction r sub u. Okay. Okay, well the first thing I know, I've seen this combination before. It's just a half the gradient of the first coefficient of the metric in the u direction. Okay, and then everything else on the right hand side is just gamma 1 1 and then ru dot ru, that's E. Okay, well let's make that clear. Okay, so I'm taking RUU, dotting it into RU. Okay, so here's RUU, and I'm dotting it into RU. So what do I get on the right-hand side? I get the gamma, RU dotted into RU. Well, RU dotted into RU, that's capital E. That's the first component of the metric. And then in the second slot here, I get RU dotted into RV. Oh, that's F, capital F, the other component of the metric. And then finally here I get N dotted into RU. Well, that's 0. So RU is in the tangent plane, N is perpendicular to it, and so I get that. And so there you go. Okay, that's the first equation, and then the second equation similarly, I get RUU dot RV. Okay, I can show that combination is FU minus a half E sub V. You know, I just fiddle with my relationships of perpendicularity and constancy for RU and RV, and I show that, and that's discussed in the tangent in the supplementary lecture 9. Okay, so that's easy. This combination is just these two derivatives of the metric. It's easy to demonstrate that. Okay, I know that F is RU dot RV. I know that E is RU dot RU, and then this collection of derivatives just reproduces that. That's all it is. It's nothing special. It's just fiddling with the inner products of RU and RV. And then on the right hand side, just like I had in the first case, a combination of Christoffel symbols and the metric, I have a similar arrangement here. Details are different. I'll leave that to you. We'll do that. We'll do the details in recitation. It'll take us a few blackboards to write it all out. But you see, now I'm all set, because now see here I have a formula for. I can think of this as a formula for this gamma and this gamma in terms of the metric. And similarly, here's another formula for the same gammas in terms of the metric. And so I have two equations and two unknowns. I can solve for gamma 1 1 and gamma 2 1 in terms of the metric and its derivatives. Okay. And then I have similar expressions for RUV and RVV. Okay. So I convinced myself by doing that Christoffel symbols can be determined in terms of the metric, and I can write down formulas for them, and you have them in supplementary lecture 9. Okay. I'll bring all of that together in a minute, but I'm not going to write down those formulas here. They're a little bit lengthy. Okay, the last thing I want to do, and it's quite necessary to complete the derivation, is to express compatibility expressions. These are the Minardi-Cadazzi equations. So for example, it just says that if I take R sub UU and differentiate in the V direction, I should get the same thing as taking R and differentiating in the U, V, and U direction. That's just that the derivatives in the U and V direction along the mesh commute. Okay, I can do them in any order, so I have to have compatibility. Okay, the compatibility is not so obvious in these expressions because I've broken up the space into a tangent space and a normal space. So I parameterize my tangent space in a particular way, and so these are going to be compatibility expressions between those parameterizations. So I have this is a compatibility expression. I have another one, RVVU is equal to RUVV, and then also I have that the normal vector, if I differentiate it in the U and then the V direction, I get the same thing as if I differentiate it in the V and the U direction. Okay. So I write all of these things out. It's a little bit lengthy. It involves the Christoffel symbols and everything like that I've written for these guys. I write it in terms of my basis at that point, the tangent plane and the normal plane, and I find expressions of the form coefficient times r sub u plus coefficient r sub v plus coefficient n hat is equal to 0. Well, all these three directions are independent, and so the three coefficients have to be independently 0. And I learned some relationships, okay, between all the objects, the Christoffel symbols, okay, and the gradients of the metric that must be there for a sensible surface, a surface that satisfies these compatibility statements. So check out supplemental lecture 9 for details, and I'll just jump to a couple of the implications. Okay, so I write all that out, okay, and I learn, for example, that minus the Gaussian curvature times the first term in the metric is this collection of Christoffel symbols. Now I solve the Christoffel symbols in terms of E, G, and F. Okay, so I can calculate all of these things. Okay, and so I can calculate an equation for K. Okay. The Christoffel symbols were obtained just in terms of the metric. So this really finishes the proof. You see, it says K is some messy bit of algebra, but it only depends on the metric. And we'll write it down explicitly in a moment. That's one that I calculate. Now you also get another compatibility result. It's a K times F is equal to this collection of Christoffel symbols. Okay, and finally my task is more algebra, to write the right-hand side in terms of the metric. Okay, and I do that, okay? In the textbook, we do that in one of the problem sets. And here I do it for the case where I have an orthogonal mesh where f is equal to 0, and I get a handy formula for the Gaussian curvature. The Gaussian curvature is minus 1 over 2 square root of e times g. And then these derivatives of the components of the metric. Okay, that's a famous formula. We're going to use it a lot of times, and it expresses Gauss's excellent theorem. You give me E, F, and G, the metric, as a function of the mesh, and I'll tell you what the curvature is. I'll just plug it in there. Okay. Okay. So the derivation was, I sketched it, rather dreadful. Okay, I admit it. Okay, there are other formulations of surfaces that get it to me more elegantly, but this is what we can do given where we are in our developments. Okay, so there's K, and here I'm just reminding you of what E, F, and G are. It's the metric. Okay. Now we've gotten some formulas before for K in terms of these things. We've done special cases already, and this is the interesting special case. Okay, so we'll really complete the discussion in recitation section, but really this is all I wanted to do with it. I want to carry away this formula, okay, and I want to move on to other topics in differential geometry. We want to turn to covariant differentiation. How do we differentiate fields, tangent fields to surfaces? Okay, and we want to prepare ourselves for the Gauss-Bonnet theorem, but we'll turn now to we'll do in recitation a section. So we'll fill in the theorem that we just sketched, and we'll do some applications of it, and get used to the concept of the Gaussian curvature. So next time in lecture, let's pick it up here and develop and see how important the Gaussian curvature is to other geometric features of a general surface.